Okay, so right now we're going to look at Unit 1, Worksheet 1, Graphing Practice. The purpose behind this worksheet is to get comfortable graphing data, interpreting data, and when necessary, linearizing data. There are 4 data sets with this worksheet. Today we're just going to talk about data set number 1. With data set number 1, we're going to first plot the data on that 10 by 10 grid to the right. We're going to use those elements of good graphs that we learned about in the reading, experimental design, and graphical analysis of data. So when we look at data set number 1, we have column 1 representing our volume. That is the variable, volume, and we measure volume with units of meters cubed. That's what the m to the power of 3 is. Our other variable is pressure. Pressure is measured with what's inside the parentheses, pascals. One of the things we would have seen in the reading is that by convention, we typically have our independent variable as the very first column and our dependent variable as the next column. One other thing that we see that we typically do when we're graphing data is that our independent variable ends up on our x-axis and our dependent variable ends up on the y. That will be important when we're setting up this graph just to try and ensure a little bit of consistency. So when we set up our graph, my x-axis will be where I have my independent variable. So I'm going to write down the variable volume. I also need to know how we measure volume. So in parentheses, I write the unit of measure. We use cubic meters to measure volume. Then after that, I'm going to see what type of scale that I need. My values of volume go from 0.1 all the way up to 10. We will almost always be starting off with 0 as our very first value. And then the maximum value should be the largest value you have associated with that variable. So I have it from 0 to 10. Then I need to break that up so that way every single one of these boxes represents the same amount of volume going left to right. There are 10 boxes here, so I take my maximum value of 10 cubic meters, and I break that up into 10 parts. I do that by taking the 10 cubic meters and dividing by 10, which gives us a value of 1. Every single one of these boxes represents 1 cubic meter of volume. So I am labeling every single box with that value. And instead of dead center of the box, we tend to use those lines to kind of guide us where we're looking at. So when I'm looking at that first line over, it's 1 cubic meter of volume. 2 lines over, 2 cubic meters, so on and so forth. This is what we're looking for when we have a fully descriptive axis. We need to do the same thing with our y-axis. This is where we're going to put our dependent variable. So I'm writing down the variable, which is pressure, and then in parentheses, the units of pressure, which here will be pascals. Then I'm looking at my scale, starting off at 0. My maximum pressure from the data that I have is 40. So my maximum value on the y-axis should be 40. There are 10 boxes there, so I take my maximum value of 40 pascals and divide it by 10. Every single box is going to represent 4 pascals of pressure. So I am labeling each one of those ticks, one of those lines, with the associated pressure measured in pascals. Just adding 4 to the previous number, so that way I have a good, clear grid, so that way I can start plotting my data points. But before that, I'm also going to include my title. A very good title that shows the relationship between these two variables is the variable on the y-axis versus the variable on the x-axis. Here, that is going to be our pressure versus our volume. You don't need to include units in the title. Now that we have set up our axes with the variable, the units, and an evenly spaced scale that uses up all of our space, we can finally start plotting our data points. The very first volume that we have is 0.1 cubic meters. So I'm going to look at the space on my x-axis between 0 and 1. And I know 0.1 is 1/10 of the way between those two values. So I'm going to put my x value really, really close to that 0. And then I'm going to go up to my y value of 40. Just to make it really easy to see, I put the dot there, but I also circle it with a point protector to make it really easy to see. The next value is 0.5, exactly halfway between 0 and 1. And then that goes up to a y value of 8. So I plot that data point and put the point protector. 1 cubic meter, 4 pascals of volume, 4 cubic meters, and 1 pascal of pressure. Oh, but wait, we don't actually have a horizontal line that corresponds with 1 pascal of pressure like we did for the previous two. This is where we just need to approximate. 1 is exactly 1/4 of the way between 0 and 4. So just visually, I'm going to try to approximate where that 1/4 of the way is going to be. Somewhere around there. I'm going to do that with the rest of these when I need to approximate the pressure that we have. So 5 and 0.8, 8 and 0.5, and 10 and 0.4. Now, we don't connect the dots because that is not going to be a good way to kind of see the trend. We do want to put a line of best fit if this is a straight line. However, the relationship that we are seeing, it's not a straight line, it seems to be curving a little bit. So what we're going to be looking at is we're going to use our graphical method summary, that other sheet of paper that was passed out the other day. We're going to try to see which of these 5 shapes our graph looks like. It kind of looks like the third one down. So that written relationship is that y is inversely proportional to x, or in real world terms, our pressure is inversely proportional to our volume. But that's not really easy for us to mathematically analyze. So we are going to use this modification required to linearize the graph to make it a straight line. So what we're graphing is y versus 1 over x. What that means is we keep the y values the same, but our new x values will just be 1 over our previous x values. So on this worksheet, we do have that blank column that we can use. The first column is our x values, the second column is our y's, the third will be our modification, which here is 1 over x. But once again, that's just in math. To make a real-world meaning, we're just going to replace the x with our variable, in this case, volume. So this last column is going to be 1 over our volume. If we do something to the variable, the same modification has to be done to the units. So we now have 1 over meters cubed for our unit of measure. Now, when we are calculating these values in this column, we just do 1 over our previous x value. So for this first one, it's 1 over 0.1, which gives us 10. Next one is 1 over 0.5, gives us 2. 1 over 1, 1. 1 over 4, 0.25. 1 over 5, 0.2. 1 over 8, 0.125. And 1 over 10 is 0.1. Now, when we have these are going to be the new things that we plot on our x-axis with that second graph, because that modification that we need to have in order to linearize it, it should be y versus 1 over x. So we keep our y-axis exactly the same. We're not going to make any modifications whatsoever. So we will still have pressure measured in pascals on the y-axis. And we can keep the exact same scale, going from 0, and by intervals of 4, we can go all the way up to 40. But our x-axis is now, instead of being volume, it is 1 over our volume. And then that will now have units of 1 over cubic meters. But if we're looking at the range of values, our maximum value is still 10. So we are going to have the exact same scale. If for some reason your maximum value is different, that happens. Just readjust the scale and make sure that it's evenly spaced. But I'm still going to go by intervals of 1 all the way up to my 10. And then we will still have our title. Now it's going to be pressure versus 1 over our volume, instead of our pressure versus volume like the previous graph. But we're going to be graphing it. The first data point I have is going to be 10, that's going to be on my x-axis, and 40 on my y. So 10 over and 40 up. The second value, 2 over and 8 up. Next one, 1 over and 4 up. Next one, 0.25 over, and 1 up. So this is going to just be another approximation. We might notice that next one's 0.125 over and 0.5 up, 0.1 over and 0.4 up. Those are going to be really, really hard to accurately place. So just try your best when we are plotting those. They're going to be basically in that same straight line. But notice, we went from that curvy shape that we have for the previous data set, and then now this one looks like it's going to be in a straight line. So what we're going to do with this is we're actually going to draw a line of best fit. This is where you would use a straight edge if you're doing this pen and paper. And then you just draw a single line that best fits your data, trying to go through as many points as possible. Like that one goes through all of these points. So that is going to be a good linear relationship. When we have it set up this way, it makes it really easy for us to calculate the slope of a straight line. So we were going to choose a couple of points that we know. I am going to choose this very last data point, and to indicate I'll be using that for my calculations, I'm putting that plus sign on it, my slope calculation point. And then I also know, well, pretty much every other point on that line, but 1, 4 seems super obvious for me, so I'm going to use that as my other data point. Now that we have chosen which points we want to use, we can actually calculate the slope of this straight line graph. So our slope is going to be equal to our change in our y values over our change in our x values. So for this last point that I have here, the x value is 10, the y value is 40. This first point that I chose, x value is 1, y value is 4. So the change in the y values, we end up at 40, and then we started off at 4. Our change in our x values, we ended up at 10, and we started off at 1. So the change in our y, we increased by a value of 36 when we had our change in our x value of an increase of 9. But those are just numbers. In order to make this a real-world meaning, we need to put our units with it. We increased 36 pascals, our units of our y-axis pressure, when we also increased by 9 1 over volume, which the units are 1 over meters cubed. At this point, we can simplify that down. 36 divided by 9 is the same thing as 4 over 1. And the units that we have with that, pascals and 1 over meters cubed. So we increase 4 pascals of pressure for every 1 inverse meter cubed. That is going to be our slope with how we are going to calculate it. And we write it with our real-world terms by including our units. When we calculate a y-intercept, we can take our equation for a straight line, y equals mx plus b, where our b is going to be the y-intercept. If we're to rearrange this, our y-intercept is equal to a y value minus our slope times our x value. So we just take a point where we know both the x and the y, and we've already calculated the slope. So I'm going to use, again, 1 inverse cubic meter and 4 pascals. That's first data point that I have there. And it's 4 for the y value, 1 for the x, and our slope is 4. So 4 times 1 is equal to 4. So I have 4 minus 4, which is equal to 0. So my y-intercept's value is 0. The units of the y-axis are pascals. So our y-intercept is 0 pascals. When we write our equation for a straight line, we start off with that format, y equals m times x plus b. Then we take what variable is on our y-axis, in this case, pressure, and replace that with our y. We take our slope that we'd already calculated and replace the m with that value. 4 pascals for every 1 inverse cubic meter, multiplied by what variable is on our x-axis. Here it is 1 over our volume, plus our y-intercept, which we calculated as 0 pascals. Now we can abbreviate this if we know what shorthand we use for the variables or for the units, but if you just want to leave it like this would be considered a correct answer. But I'm going to shorthand this. Our pressure we can represent with a capital P. Pressure is equal to 4 pascals. We already have capital P for pressure, so we want to differentiate that. So we'll do PA for our unit of pascals. And then we have 1 over 1 cubic meter, because that's already abbreviated, times 1 over a capital V for volume, plus our 0 PA for the 0 pascals of pressure when we have 0 inverse cubic meters of volume. So this is going to be our equation of that straight line graph. So to summarize what we did, we first looked at our data sets. We remembered that our first column will typically be our independent variable, which is typically plotted on the x-axis. We use that variable of volume and the units, cubic meters, to label the axis, and we set up an even scale. We did the same thing with the second column, which is typically going to be our dependent variable, which typically goes on the y-axis, to label it with the variable, pressure, the unit, pascals, and an evenly distributed scale. We set up the title, so it's the y-axis versus the x-axis, in this case pressure versus volume. Then we plotted the data points. We used our graphical method summary to identify which graph shape our data looked like, and then we used that modification to linearize graph to linearize the graph. This relationship between pressure and volume is inversely proportional. So we needed to do the inverse of our x values to linearize it. That's what that third column was for. Our new variable is now 1 over volume, and those new units are 1 over cubic meters. We ended up doing the same graphing with that new set of data, but because we linearized it, we ended up with that straight line graph. From the straight line graph, we were able to calculate the slope, the y-intercept, and write an equation for the straight line graph. That final equation was written in real-world terms by replacing our y and x variables with the real-world variables we used, pressure and inverse volume proportionally. And then we ended up using our slope, which we calculated, written with units, 4 pascals of pressure for every 1 inverse cubic meter, and our value for the y-intercept of 0 pascals to end up converting that y equals mx plus b into a physics equation that is written in real-world terms.